Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center and is broadcast by Pagama Research and Development. Remember, we have a WhatsApp interactive number 064 748 8913. 064 748 8913. You can use that number to interact with us. Right, today we are looking into the applications of calculus. Just like you've done derivatives and you've done average gradients, we are now looking into applying calculus in real world situations. Right. By the end of this lesson, you should be able to solve optimization problems involving shapes, solve optimization problems involving graphs, solve problems involving rate and motion. Right, you can refer to the CAPS document on page 32 and also on page 46, and also the exam guideline published in 2021 on page 7. The pre-knowledge that you must come with to this lesson is the knowledge of measurements, average gradient, rules of differentiation, understanding the meaning of the derivative, higher order derivatives, and finding minimum and maximum values. Right, let's just look at the background of this topic. In this section, we are interested in minimizing or maximizing a specific function. This function would be given to us. That would be direct application of calculus if the function is given to us. Or we'll have to formulate our own function. If we formulate our own function, it would be an indirect application. In order to optimize the function, we will need to determine the value of a specific variable. In order to determine the minimum or maximum values, we differentiate the function and set it to be equals to 0. Just like you were doing when you were finding the turning point of a third-degree function or the cubic function. In this section, we will also be determining the rate at which one variable changes with respect to another. It is important to note that in order to find the rate of change of a function at a specific moment in time, we should be calculating the derivative of that particular function at a point, but it's important to note that we do not set that particular derivative to be equals to 0, because that would mean we are equating the rate to 0, or we are saying that it's a minimum, or we're finding a minimum or a maximum value, or the value of a variable to which the minimum or maximum occurs. Now, in this lesson, we are going to be focusing on 3 parts of application, or 3 main sections of application, although there are 4 in nature, because we also have our application to word problems. But for specifically this lesson, would do 3 application problems. We apply our knowledge of calculus to shapes, we'll apply it to graphs, and we'll also apply it to rate, including the calculus of motion. Right, application to shapes. Obviously, from grade 10 and 11, you use your knowledge of mensuration to derive some of the formulas that you see here. We have right prisms, right pyramids, right cylinders. We have the formulas that we can use there to calculate the volume as well as the total surface area. Now we have a right cone, we have a sphere, and we have a hemisphere. Now it's important to note here that according to the exam guideline, you should know the formula and surface area of right prisms. All right prism formulae should be known by heart. You should be able to do that. they will not be provided to you. Those formulas will not be provided to you. However, the list of formulae to choose from will be provided to questions based on cones, spheres, and pyramids. In all those figures that involve slant heights, you'd be given the formulas to choose from, and you should be able to select the correct formula and use it to solve a specific question that you'll be given. Right, let us look at the first example. First example, we are applying our knowledge of optimization. We want to apply that to two-dimensional shapes. Now, the first question asks of us to show that the area is given by that function. Now, if you check here, this would be a direct application because you are given, or rather you are asked to prove that the objective function is given by a is equals to 100x minus pi x squared over 4. So we are interested in showing that that objective function would be 100x minus pi x squared. Now, if we are to look into this specific question, it says equal semicircles on sides A, B, and DC are cut out of a rectangle ABCD. So what is happening here is that we are cutting out equal semicircles on opposite ends of this particular rectangle. BC stays fixed at 100 millimeters, while AB varies. If AB is x millimeters, if AB is x millimeters, show that the area left is given by 100x minus pi x squared over 4. Now, if you check, the shapes that are removed in this case are semicircles, and it's two of them. So if it's two semicircles that are removed, then it means that it would be a complete circle, because they said that those semicircles are equal, so they would form a full circle. So it's like we are removing a full circle, but we're removing that circle in semicircles on the opposite ends of this particular rectangle. Now, it means that if we are to formulate our area that is left, it should be the area of the original rectangle, subtract the area of the two semicircles that were removed. So we should have that it should be the area of a rectangle, subtract the area of two semicircles. If it's two semicircles, then they would make 1 circle or a full circle. Now, what is the area of a rectangle? The area of a rectangle is given by length multiplied by breadth, and the area of the circle is given by pi r squared. Now, if we look at the length of this, can see that it's given by 100 millimeters, while the breadth of the width is given by x. Subtract pi, the radius. We are now looking for the radius of the circle. So this is the circle that was removed, and we can see that from A to B, you get that this is equals to x. The diameter of this is equals to x. However, we are looking for the radius, which is the length from the center to the circumference. We know that 2 times the radius will always give us the diameter. In this case, the diameter is x. So 2 times radius is x, which means that the radius would be half of x, or x over 2. That would be our radius in terms of x. Now, our radius is given by x over 2 all squared. Now, if you multiply or you square the terms in the brackets, you'd have that you square the numerator, you get x squared, and you square the denominator, you get 4. So we are done here. We showed that our objective function is given by 100x minus pi x squared over 4. Right, moving right along. Determine the maximum area and the corresponding value of x. Now, they are bringing in the word maximum. We want to maximize the area. And in order to maximize, remember when we started with our background, we said we need to differentiate that objective function, and then we equate the derivative to be equals to 0. We'll find the value of the variable to which the maximum area would occur, and then we use back substitution to determine the maximum area. Now, from Roman figure 1, we obtained that the area is 100x minus pi x squared over 4. So we want to differentiate, which means that we need to find dA dx. Remember, your knowledge of notation here is also important because we are differentiating a with respect to x. So dA dx should be given by, this should be 100. If you differentiate 100x, you get 100. Minus, if you differentiate pi x squared over 4 with respect to x, you should be getting 2 pi x over 4. Now remember, max occurs, or the maximum occurs when dA over dx is equals to 0. The maximum would occur when the derivative is equals to 0. Now, it means that we would have 0 is equals to 100 minus 2 divided by 4. That should be pi x over 2. If you transpose, you're going to get that pi x over 2 is equals to 100. If you solve for x, you get that x should simplify to 200 over pi. X should simplify to 200 over pi. If you put that in your calculator, obviously you should get something around 63.66 millimeters. That is the value of x for which the maximum will occur. Remember, when you have pi, you should only put it into the calculator for the final step so that you don't lose any decimal points along the calculation. Now, you found the value of x for which the maximum occurs. Now, the question was, we need to determine the maximum area, which means that we come back to the objective function. The objective function in this case is a is equals to 100x minus pi x squared over 4. Already you know the value of x to which the maximum occurs. We know that that value of x is 200 over pi. So this is 100 into 200 over pi minus pi into 200 over pi all squared divided by 4. Now, your max area in this case should be, when you substitute everything into the calculator here, you should get 3183.10 square millimeters. That is the area. That is the maximum area. We know the value of x to which the maximum area occurs. We use back substitution to find the maximum area. Right, let me explain again what we did. We worked with our objective function. We were supposed to find an objective function or prove that an objective function is of a given nature. We did that. And then from there, they wanted us to determine the maximum area. For us to determine the maximum area, we differentiate, set our derivative to be equals to 0. And then from there, we find the value of x to which that maximum occurs. Then we use back substitution, substituting back to the objective function to get the maximum value of a. Remember, maximum or minimum, you differentiate and set the derivative to be equals to 0 because at the maximum, the gradient of that particular function is equals to 0. Right, moving on to example 2. Moving on to example 2, we are now moving to 3-dimensional shapes as opposed to the 2D shape that we worked with. Now we are looking at a 3D shape. A soft drink has a volume of 340 cubic centimeters, a height of h centimeters, and a radius of r centimeters. Express h in terms of r. So they want us to express our height in terms of the radius. Express h in terms of r. Now, if you check what we are given here, we are given the volume. We are given the volume of this cylinder. Now, we know that the volume of a cylinder is given by the area of the base multiplied by height. The area of the base in this case is pi r squared multiplied by height. Remember, these formulas, you should know them by heart. They won't be given to you in the formula sheet. You should know them. We are talking about right prisms in this case. The formulas should be known. So now this is the formula for the volume. The reason why I'm reverting to volume in this case is that in the question they gave me the volume of this particular cylinder. Now, if I substitute, I will have that 340 is pi r squared over pi r squared multiplied by h, which means that if I want h, I'll divide uniformly throughout by pi r squared. So I'll get that h is 340 divided by pi r squared. So I've expressed h in terms of r. I've expressed h in terms of r in this case. Right, moving right along. The second question, show that the total surface area can be given by this objective function. A of r is pi r squared plus 600 r to the minus 1. Now, if you check, the area is only given in terms of r. It is only given in terms of r. Now, they want us to work out the total surface area. We know that with these figures, if we want the total surface area, then we are looking for the surface area of all the shapes that make up this particular cylinder. So if we can open up this cylinder, we get that it should look this way. That is, if we open it up to show all the shapes that make it up, or that make up this particular cylinder. Now, this is our height of the cylinder, and then we have that this would be our radius r, and this is our radius r. Now, in order for us here to work out the total surface area, it means that we should be adding all the areas that are involved in this case. So we have that our objective function a of r should be given by, if you check here, we have 2 circles, so it's 2 times the area of the circle plus the area of the rectangle. This part here is a rectangle. So we have 2 circles and a rectangle that make up this cylinder. Now, the area of the circle obviously is given by pi r squared. So this is 2 pi r squared plus the area of the rectangle, which is length multiplied by breadth. The length in this case would be the circumference of this circle, 2 pi r multiplied by h. That would be the breadth of that particular rectangle. Now, if you check, this objective function has h in it. The one that I just wrote has h in it. And our aim is to write the objective function in terms of r only. That is why the first question asked of us to express h in terms of r. Obviously, we know what h is in terms of r. So this is 2 pi r squared plus 2 pi r. H is given by 340 over pi r squared. Now, continuing with this, we have that this is 2 pi r squared plus, obviously, the pi and the pi is going to divide out. This r is going to go to the r squared once. 2 times 340, that should be given by 680 divided by r. Now, if we use the inverse law on the r that is on the denominator, the inverse law of exponents, 2 pi r squared plus 680 r to the minus 1. This is the objective function a of r. So now we've proved that a of r is given by 2 pi r squared plus 680 r to the minus 1. So we are done with the second part of this. We move on. Now determine the radius of the cone that would ensure that the surface area is a minimum. So now we are interested in the value of r. Determine the radius. Remember the previous question in example 1, they said determine the maximum area. So we started by finding the value of x to which the maximum occurs, and then we found the maximum. In this one, they're asking us to determine only the radius that would ensure that the surface area is a minimum. They did not say we need to calculate the minimum surface area. They're just looking for the value of r to which the minimum would occur. Now, it means that we have to then differentiate a of r, a dash r, or a prime of r. We need to differentiate our objective function in terms of r. So if we differentiate in terms of r, remember pi is a constant. So pi is treated just like any other number. It is just a constant. So we differentiate with respect to r. It means we'll differentiate the r squared. We get that this is 4 pi r. That is if we differentiate the first part. And then differentiating the second part, we get minus 680 r to the minus 2. Remember, minimum value occurs when a prime of r is equals to 0. It occurs when the derivative with respect to r is equals to 0, which means that we'll now have 4 pi r minus 680 over r squared is equals to 0. I used the inverse law again on the r to the minus 2. Now I can transpose the 680. I get 4 pi r is equals to 680 over r squared. Now I multiply by the LCD, in this case the denominator r squared, both sides. I'll get that this is 4 pi r cubed is given by 680. We need to solve for r. Continue with it here. We need to solve for r, so we'll have that r cubed would be given by 680 divided by 4 pi. 680 divided by 4 pi, which means that r should take the cube radical of 680 divided by 4 pi. That's what we have there. If you put this into your calculator to get the value of r, you'll get that the value of r simplifies to 3,78 centimeters. So you've worked out the value of r that would ensure that the surface area is a minimum. So we move on. Right, now we are applying this to a cone. This is a cone. It means that the formulas to work out the surface area and the volume would be given to you, and you just have to choose. If you are given a series of formulas, maybe 4 formulas, then you need to just select the correct formula to use to find either the surface area or the volume. Now, the diagram represents the right circular cone of height h centimeters and a base radius of r centimeters. If the sum of the height and the base of the radius, or the base radius, is 12. So we're given the sum of the height, the perpendicular height in this case, as well as the radius. It's given by 12. So if we are to interpret that, we are given that the sum is the answer we get when we add. So the sum of the height as well as the radius should be equals to 12. Now the first question wants us to express r in terms of h. So we need to write r in terms of h, not h in terms of r. So we're going to then transpose or the h, so we have that this is 12 minus h. We've expressed r in terms of h. That's what we wanted to do for first one. The second one, express the volume of the cone in terms of h. Express the volume of the cone in terms of h. Remember from the first one, we worked out that r is 12 minus h. They want the volume in terms of h. If you check from the formulas that I gave you earlier on, the volume of a cone should be a third of pi r squared h. That should be the volume of the cone. It should be a third of pi r squared multiplied by h. This formula will be given to you. So now what we do is we have a third pi. We've worked out that r is given by 12 minus h all squared. That is r is given by 12 minus h all squared. So where we see r, we put 12 minus h. Now, this is a third. We now simplify pi h into, obviously, if we open these brackets, we square the first term, we get 144. Twice the product, that would be minus 24h, plus we square the last term, that should be h squared. Now, if we distribute this, then we should be obtaining 144 divided by 3 multiplied by pi h. 144 divided by 3 multiplied by pi h in this case. You should be able to put that in the calculator and see what it gives you. So this should be 48 pi h, and then you distribute again 1 over 3 pi h multiplied by 24h. In this case, you should be getting minus 8 pi h squared. And then the last one, you distribute again, you get a third of pi h cubed. That's what you should obtain in this case. That's what you should obtain. So you've now expressed the volume of this particular cone in terms of h. Now moving right along. Now the last one, determine the maximum volume of the cone. So they want us to determine the maximum volume. Remember, we said to maximize, we differentiate and set that particular derivative to be equals to 0. Now, I'm going to give you about 3 minutes to determine this maximum volume. Going to give you 3 minutes to try and work it out. You use the same method that I've used in the previous 2 examples and find the volume for me. Your time starts now. Hello and welcome back. Right, I asked you to work out the volume, the maximum volume of the cone. So let's go through it together and see whether you managed to get it correct. Right, remember to determine the volume or the maximum volume, we need to differentiate first. So we differentiate V in terms of H. dV over dH, this would be equals to, this should be 48 pi. Remember, we are differentiating with respect to h. So this should be 48 pi minus, if we differentiate 8 pi h squared with respect to h, this would be 16 pi h. And lastly, if we differentiate a third of pi h cubed, this should simplify to pi h squared. That's basically how we differentiate this expression. Remember, the maximum occurs when dV over dH is equals to 0, when the derivative is equals to 0. Right, which means that we now have to set the derivative to be equals to 0. So what I'll do is, if we check here, all the terms contain pi. All the terms contain pi. So I'll divide all the terms uniformly throughout by pi. So which means that I will be getting 48 minus 16h plus h squared is equals to 0. So if you look at this, you see that this is a quadratic equation. So we can write it in standard form. H squared minus 16h plus 48 is equals to 0. So we've written this quadratic equation in standard form, and now we want to find the value or values of h, which means that we have to factorize this quadratic equation. We can do so using our inspection, of course, or using the quadratic formula, or we can also use the method of completion of the square. So if we use inspection, we look for the factors of 48 that can give us 16. So this is h and h. So that would be 12 and 4. Because the last term is positive, both the terms would be negative, or they will carry the same sign, which should be the same as the sign of the middle term. So we work out that h is equals to 12 or h is equals to 4. So we get two values of h that can give us a maximum according to this. However, if we go back and check here, they said the sum of the height and the base radius is equals to 12. The sum of the height and the base radius is equals to 12. So h on its own cannot be equals to 12. Because remember, in order for us to get this sum, and in the first question, we expressed that if the sum of the two, the sum of the height and the radius is equals to 12. That's what we are given. So h plus r is 12. So h on its own cannot be equals to 12. Because the sum, when you add it to the radius, that's when you get 12. Which means that 12 will be excluded from this solution set. And then the only value that would carry forward is h is equals to 4. Right, remember they said we need to determine the maximum volume, which means that we have to then use back substitution to get the maximum volume, which means that we'll be substituting 4 on our objective function. So V would be equals to 48 pi times 4 minus 8 pi times 4 squared plus 1 over 3 pi times 4 cubed. That is how we get our maximum volume. So we'll say that max V would be equals to, you then put everything in your calculator to get the maximum value, you will find that it is given by 268,08 centimeters. That would be the maximum volume of the cone. That would be the maximum volume of the cone. Right. We are done with this particular example. We move on. Application to graphs. Remember, with shapes, we said what is important is that we know all the formulas of the right prisms, but when it comes to cones, pyramids, and spheres, would be given the formulae in the question paper, or within the question they will attach formulas that we can choose from. So that is the first thing that we need to be able to do as far as shapes are concerned. And then we will then use that knowledge to formulate a function in terms of one variable, and that function is going to be our objective function, which we can either minimize or maximize by differentiating and setting the derivative to be 0. Find the value of the variable to which the maximum or the minimum occurs, and then you can use back substitution and substitute back to your objective function to find the value of the maximum or the minimum area if you are working with areas. If you are working with the volume, you would find the minimum or the maximum volume. That is how you need to operate when you work with shapes. So it's very, very important that you go back to your grade 10 and 11 knowledge of measurement and revise measurements. Make sure that you understand all the fundamental concepts that are involved in mensuration, so that you'll be able to apply your knowledge to calculus. Right. Moving right along. Right. I want you to look at this problem and try to work with it for 5 minutes, and then we'll come back and solve it together. Your time starts now. Welcome back. Right, let us look at this problem that I gave you. Let's try to work through it together. The line with an equation x plus y is equals to 4 and the graph of the function xy is equals to 1 for x is greater than 0. So x is positive in this case. Are represented in the diagram alongside. Line segment PQ varies in length between the 2 points of intersections of the graphs. Determine the maximum length of PQ. So this takes us back to our lesson on interpretation of sketched functions. We are looking at the vertical distance, in this case PQ, or the distance between two graphs, and we said in order for us to determine the distance or the length between two graphs, we take the top graph minus the bottom graph, or the y value at the top minus the y value at the bottom in this case. So we have two equations. One is an equation of a straight line and the other one is an equation of a hyperbola, and both equations are not written in standard form. So the first thing that we're going to do is we write the equations in standard form. The first one is x plus y is equals to 4. If we write this in terms of y, then we're going to have that y would be equals to minus x plus 4. Now this is in standard form. Y is equals to minus x plus 4. And then we have xy is equals to 1. And then if we divide uniformly throughout by x, we get that y is equals to 1 over x. Y is equals to 1 over x. So we've written both equations in standard form. So to get the length of PQ, the length of PQ is a vertical distance between two graphs. So it's the top graph minus the bottom graph, or y top minus y bottom. So we have that this would be the y top minus y bottom in this case. Y top would be the top graph in this case is our straight line. So we have minus x plus 4 minus 1 over x. So we get that now our PQ is given in terms of x only. So if I use the inverse law here, I would get that this is x to the power of minus 1. Now, the question wanted us to determine the maximum length of PQ. So in order for us to maximize, we differentiate PQ with respect to x, and then we find the value of x to which the maximum length occurs, and then we can use back substitution to find the maximum length of PQ. So if we work out the PQ dx, this would be equals to minus 1 plus the derivative of negative x is minus 1. The derivative of 4, which is a constant, is 0. And the derivative of x to the minus 1 would be plus x to the minus 2, to the power of minus 2. Obviously, we need to set the derivative to be equals to 0. The PQ dx is equals to 0 if we want to get the maximum length. So now we transpose the 1, we're going to get that 1 over x squared is equals to 1. Simplifying this, we get that x squared is equals to 1. We continue with it here. X would be plus minus the square root of 1. So x would be 1 or x would be minus 1. Now going back to the statement there, they said x should be greater than 0. X is positive. Even if that statement was not given, if you check from the graph itself, you see that the graph lies in the first quadrant where both x and y are positive. So we are going to exclude minus 1. Now we have the value of x to which the maximum length occurs. So to find the maximum length, we then say max PQ will be equals to, we use back substitution. We substitute the value of x back to the objective function. The objective function in this case was PQ is minus x plus 4 minus x to the power of minus 1. So this would be minus into 1 plus 4 minus 1 to the power of minus 1. So this would be 4 minus 2, which is equals to 2 units. The maximum value of PQ that we can get would be given by 2 units. Right, that is the first application to graph. Distance between two graphs, top graph minus bottom graph, or y top minus y bottom. And then from there, it would be in terms of x only, or that equation, the objective function would be in terms of x only. So you can differentiate to get the maximum and equate the derivative to be equals to 0. Right, moving on, we get another example that involves application to graphs. In the diagram alongside, the graph of f of x is 18 minus x squared is drawn. ABCD is a rectangle drawn within that particular parabola. And B, with A is axis to y, and B on the parabola. Points C and D lie on the x-axis. Now, if you check this problem, it's an integration between application to shapes and application to graphs. We have a two-dimensional shape in this case, which is a rectangle, and then we have a parabolic function. So we are integrating our knowledge of application to shapes with our knowledge of functions as well as application to functions. Now they say determine the coordinates of A and B in terms of x. Determine the coordinates of A and B in terms of x. Now, if you check the coordinate of A, the abscissa is x, and the ordinate is given by y. And this point A lies on the parabola. And we know that there's a relationship between the x and the y values of the parabola given as an input function that is given there. So we have the function here that gives us the relationship between x and y. It says y would be equals to 18 minus 2x squared. So where we see y in this case, we can put 18 minus 2x squared because it lies on the parabola. If the abscissa is x, then the ordinate would be governed by that particular equation. So we've worked out the coordinates of A. Now they want the coordinates of B. Now if you check B, along that line, along the line AB, y does not change. It is only x that changes. Y does not change. It is only x that changes. Now, how does the x change? If you check, this is a parabolic function, and its axis of symmetry is x is equals to 0. So the points on the left are symmetrical to the points on the right in this case. So if the abscissa of point A is x, then the ordinate or the abscissa of point B would be given by negative x. We are using symmetry in this case. It would be given by negative x. That is, x is changing along this horizontal line. X is changing, but y remains the same. So if y remains the same, then we know that y was given by 18 minus 2x squared. So those are the coordinates of A and B. Those are the coordinates of A and B. Right, let me repeat quickly. Along the line BA, the value of y does not change. That is why the ordinate here is 18 minus 2x and the ordinate there is 18 minus 2x. However, the values of x are changing. So we want to know by how much. Now, if we have the symmetrical line or the axis of symmetry, we are given the axis of symmetry because this is a parabola. We see that the axis of symmetry is x is equals to 0, which means that the points on the left are equidistant to the points on the right, which means if the abscissa of point A is x, then the abscissa of point B would be minus x using symmetry. Right, now they want us to determine the area of ABCD in terms of x. The area of ABCD in terms of x. Now, if I can write down this rectangle, we know that the coordinates of B, we've written them as minus x is to 18 minus 2x squared. And the coordinates of A is x is to 18 minus 2x squared. And then the coordinates of C, if we can find the coordinates of C, we see that C is on the x-axis, which means that y is equals to 0. But along the line, the vertical line BC, you can see that x is not changing. It is only y that is changing. So the abscissa at B should be the same as the abscissa at C, which means that the coordinates of C would be minus x is to 0. Similarly, when we go to point D, AD is a vertical line. AD is a vertical line, and along line AD, x is not changing. It is only y that is changing. X is not changing. So, which means that the abscissa at A should be the same as the abscissa at D. The x value at A should be the same as the x value at D, because along that line, x is not changing. It is only y that is changing. So, but this line is also on the x-axis, which means that the y value is equals to 0, but the x value in this case is x. So we have all the coordinates of ABCD, the rectangle ABCD, which means that we can be able to work out the length as well as the breadth of this particular rectangle. Now, if we want to work out the length CD, this is A, B, oh no, this is B, C, D, A. If we want to work out the length of CD, remember we are moving from minus x to x. In order to do that, we need to move 2x units. And to move from A to D, remember this, because it's a rectangle, opposite sides are equal, which means this is also 2x. Now, if we want the length of AD, we are moving from x is the same, which means that only y is changing. So it will be y top minus y bottom. That would be 18 minus 2x squared. Also this side 18 minus 2x squared. So we have both the length and the breadth of our rectangle. We then want to work out the area of that rectangle in terms of x. So area would obviously be length multiplied by breadth. We have 2x multiplied by 18 minus 2x squared. So this should be 36x minus 4x cubed. 36x minus 4x cubed. That would be the area of ABCD in terms of x. Right, moving right along. Obviously, we worked out the area as 36x minus 4x cubed, and they want us to determine the largest possible area of ABCD. Largest possible area of ABCD. So they want the maximum area of ABCD. Now, I want you to work it out using the knowledge that you've just gained, and calculate the maximum area or possible area of ABCD. I'm going to give you 2 minutes to do that, and your time starts now. Welcome back. Right, I gave you a problem to try out here. I said you need to work out the largest possible area of A, B, C, D. Right, let's go through that together. Remember, largest possible, they are looking for the maximum area. So we'll have that this is dA over dx. We differentiate A with respect to x here, we'll get 36 minus 12 x squared. 36 minus 12 x squared. Obviously, to get the largest area, we set the derivative to be equals to 0. So we have that if we transpose, we get 36 minus, or 36 is equals to 12 x squared. If we divide both sides by 12, x would be plus minus the square root of 3. X would be plus minus the square root of 3, which means x is root 3 or x is minus root 3. Obviously, we're only going to take the positive one in this case. Now, to get out the maximum area, we then work out max area would be given by 36 times the root of 3 minus 4 the root of 3 cubed. If you put that in your calculator, you should be able to obtain 41.57 square units for the area. Now let me get back here. We said we're going to only take the positive one. We don't take the negative one, because if we substitute that negative one, we might get that the area is negative. So we should only take the positive, because we are talking about length in this case, and length is always positive. Right. Moving right along. The rate of change. We are now moving to the last part of this. We are dealing now with rate of change. In rates, I indicated earlier when I started the lesson that we want to find the rate at which a certain objective function changes. We want to find the rate at which a certain objective function changes. So to determine the rate, we need to differentiate. That's the main idea. We differentiate, but we do not set the derivative to be equals to 0, because that would mean we are saying the rate is equals to 0. Or that would mean we are minimizing or maximizing a particular objective function. And that is not the aim in this case. The aim is to determine the rate, or the equation that would be used to work out the rate, or how a particular objective function changes with respect to time in this case. Now, example 1, the mass of a baby in the first 30 days of life is given by. So we're given the mass of the baby, and it's given by that objective function. So this is a direct application problem. Usually, rate of change and calculus of motion are described as direct application of calculus, because you are mostly given the objective function, and yours is to just work with the objective function that is given. But if you saw earlier on, when we applied the knowledge to graphs, when we applied the knowledge to shapes, we were not given the objective function. We were asked to prove that the objective function is of a given nature in shapes, and also in graphs. We came up with our own objective function, which means that those application problems are indirect application problems, where the objective function is derived or worked out by us. Now, moving right along here, they say write down the mass of the baby at birth. So here we need to be very much open-minded. Write down the mass of the baby at birth. Now, we know that T is the time in days, and M is the mass of the baby in grams. So at birth, what would be the time? What should the time be at birth? They said is the time in days. Obviously, the baby, when the baby is born, the baby does not have a day in this world. So t should be equals to 0 because it's just at birth. So that is why I'm saying you need to be open-minded in this case. So we are looking for m of 0. That is at birth when t was equals to 0. So m of 0 in this case would be equals to 3,000 grams. 3,000 grams. So that is what we're going to have there, 3,000 grams, because if everything is 0 here, 0 there, then we're left with 3,000. So at birth, the baby has a mass of 3,000 grams. Now, a baby's mass usually decreases in the first few days after birth. On which day will the baby's mass return to its birth mass? Remember, the baby's mass is m of t. So they're asking in which day or on which day will the baby's mass return to its birth mass. So which means that we need to substitute the birth mass on m of t, the function. So the birth mass is 3,000. So we would have that this would be 3,000 is equals to t cubed minus 9t squared plus 3,000. We're substituting 3,000 there because they said the baby's mass returns to its birth mass. And we just worked out the birth mass in the first question. So now we just need to solve this. We get that this is t cubed minus 9t squared is equals to 0. T into, we factor out t squared in this case. If we factor out t squared, we're going to get t minus 9 is equals to 0. So t is 0 or t is equals to 9. So we have two values of t. If we can just go back and back substitute these values, you'd find that they both give you 3,000. So on which day will the baby's mass return to the birth mass? Obviously, the birth mass is t 0 on the day when the baby was born, and we are looking for this one. So it would be on which day? On the 9th day after birth. On the 9th day after birth, the baby's mass returns back to the original mass or to the birth mass. Right, moving on. On which day will this baby have a minimum mass? Remember, on which day? We said t is the time in days, so you are looking for t. On which day will the baby or will this baby have a minimum mass after birth? On which day will the baby have a minimum mass after birth? So we want to minimize. How do we minimize? We differentiate, set the derivative to be equals to 0, and solve. That is how we minimize. So we're going to find m prime t. M prime t would be 3t squared minus 18t. Then we need to set that to be equals to 0 because we want to find the minimum mass. So if we set that to be equals to 0, then we'd have and divide by, oh no, let's just work this out as 3t squared minus 18t is equals to 0. Obviously, t is common. Obviously, t is common. Let's check whether 3 is common as well in the calculator. 3 is also common, so we can take out 3t as a common factor. So we'd have that this t minus 6. T minus 6. So t is equals to 0 or t is equals to 6. Therefore, if you go back and substitute, you'll find that t is equals to 6, which implies that on the 6th day, on the 6th day, the baby would have the minimum mass. If you want to be sure, you can go back and substitute 0 on the original equation. You'll get 3,000 But if you substitute 6, you'll get a value that is less than 3,000, which would then be the minimum. So it's on the 6th day. Now, the last question, on which day will the baby's mass be decreasing the fastest? So it decreases the fastest when m double prime of t, we find the second derivative now of this equation, which means that we have 9t minus 18. We differentiate the equation twice, which means we'd have 9t minus 18. Just like you do when you find the point of inflection. When you find the point of inflection, you differentiate twice. So even here, when you want to find out when the baby's mass is decreasing the fastest, you differentiate twice and set that derivative to be 0. So 9t is equals to 18, which means that t would be equals to 2. If you divide both sides by 2, t would be equals to 2. Let me just check here. If we differentiate, no, made an error here. If you differentiate this for the second time, we had 3t squared minus 18t. The derivative of 3t squared is 6t. So this is 6t minus 18. I made a mistake and wrote it as 9t. It should be 6t. And then we equate that to 0, which means that 6t is equals to 18. And then from there, you divide both sides by 6. You get that t is equals to 3. Therefore, on the third day. So that is what we have for the first problem. Right, moving right along. Second one, still rate of change. A water tank has both an inlet and an outlet which regulate the depth of water it contains. The depth d in meters is given by the function d of t, which is 3 plus half of t squared minus a fourth of t cubed, where d is measured in meters and t is measured in hours starting from 8. So we are measuring the time in hours, but we start at 8 o'clock. So they say calculate the depth of water at 8. Calculate the depth of water at 8. Remember, at 8, that's where we start. So that should be d at 0. That's where we start. We start at 8 o'clock. So t would be equals to 0 there. And then this would be 3. So the depth would be 3 meters. That would be the depth. It would be 3 meters because they said determine the depth at 8. And we said here we start exactly at 8, which means that, remember, they said time is measured in hours. So at 8, no time has lapsed in this case. The time that has lapsed is 0. So that's where we substitute 0, where we see d, or where we see t, I should say. Now calculate the rate at which the depth is changing at 11. Calculate the rate at which the depth is changing at 11. So we want to calculate the rate. Remember, we said to determine the rate, we differentiate. So we'll get d prime of t, which is the derivative of 3 is 0. The derivative of half of t is t. And the derivative of 1 over 4t cubed is 3 over 4 t squared. 3 over 4 t squared. And they said to us, we determine the depth at which the rate is changing at 11. Remember, time is measured in hours. If we started at 8, then it would be 8, 9, 10, 11. So it's 3 hours that has lapsed, which means that t is equals to 3 hours. At 11, 3 hours has lapsed, which means that we will then substitute 3 where we see t. We substitute 3 where we see t, because at 11, only 3 hours has lapsed. Now, using your calculator here, you will get that the depth is minus 3,75 meters per hour. That is minus 3,75 meters per hour. That is how we determine the rate at which the depth is changing at 11. Remember, the equation d prime t is the equation for the rate of change of depth with respect to time. And then they want us to work out the exact value of the rate, which means that we need to know how many hours have lapsed from 8 to 11. That is 3 hours. Now, moving right along, what happens to the depth of the water at 11? Now, if you check from the previous one, we got that our rate is negative 3,75 meters per hour. This is telling us that we have, this is the gradient, and the gradient is negative. We have a decreasing function in this case. So this is telling us that the depth is decreasing because the rate of change of depth is negative. So the gradient is negative, which means we have a decreasing function. But now this is practical. Now we are speaking of depth, and we got that the rate of change of depth is negative. If the rate of change of depth is negative, it means that the depth of water in that particular tank is decreasing. At what time will the rate be a minimum? At what time will the rate be a minimum? What should we do now? To get a minimum, we differentiate and we set the derivative to be 0. So d prime t would be, we differentiated that, we got that it's t minus 3 over 4 t squared. So because we want a minimum, we set that derivative to be equals to 0. Minimum occurs when the rate of change is equals to 0. So now to solve for this, obviously we are going to take out t as a common factor. So we get that this is t into 1 minus 3 over 4t is equals to 0. So t is equals to 0, or 3 over 4t is equals to 1, which means that t is 0 or t is 4 over 3. So we worked out those times, but the question is at what time, not after how many hours. We need to be very, very careful. Here they gave us the starting time as 8. And then the t in the objective function is the number of hours that it takes for a specific thing to happen in this, or something to happen to the objective function in this case. T represents the number of hours. Now, if we started at 8 and we want to know, this question says at what time. We want to know exactly at what time. We don't want to know the number of hours it took. And in the equation, or these values that we just got, these values of t that we got are the values, the number of hours it took for the rate to be a minimum. We are not looking for that. We are looking for the time, the exact time to which the rate is equals to 0. Now, if you check, they said time is in hours. Here you got 4 over 3 of an hour. So what we can perhaps do here is we can convert this 4 over 3 of an hour to minutes. If we convert this to minutes, 4 over 3 times 60, because there are 60 minutes in every hour, we get that this is equals to 80 minutes. And now we know, if it's 80 minutes, we know that it's 1 hour and 20 minutes. That is 80 minutes. It's 1 hour and 20 minutes. Now, we go back and answer our question. It took us 0 hours, or it will take us 1 hour and 20 minutes for the rate to be a minimum. If it's 0 hours, then it is at, therefore, coming back using this space, therefore, if t is equals to 0, then it's at 8. Remember, we start measuring at 8. So it is at 8, or if t is 1 hour and 20 minutes, then from 8 you count 1 hour and 20 minutes. It should be at 20 past 9. 9:20. 20 past 9. Right, that is how you get to the time to at which the rate would be a minimum. So the trick here was that you were given the starting time, and the question said at what time. The question did not ask after how long, it asked at what time. So we needed to go back and check the starting time as well as the time that it took for us to be able to work out the solution to that particular question. Now we are moving on to the calculus of motion. There are so many concepts here that need to be understood for us to thoroughly comprehend calculus of motion, right? I'm just going to start and move along with these concepts here. This is what I'm doing. I'm giving you a number line, or a straight line in this case, giving you the point. I'm starting at point A at the origin. I can move certain units to the left and to the right. If I move to this direction, then this becomes negative. So I move from A to B. I can also move from A to C. Now we're going to describe concepts like displacement, distance, speed, velocity, and acceleration. These are the concepts that are used in the calculus of motion. Now, I want you to understand these concepts so that you can be able to respond to questions about these specific concepts. Now, we talk about displacement. Displacement is simply change in position. Moving from one point to the next, you are changing your position. We're going to locate your final position and say he's on this particular position now. And then distance is simply the length of the path that is taken. The length of the path that is taken. Remember, we said length is always positive when we worked with analytical geometry. We said length is positive. Also, when we worked with functions, when we found the length of functions, we said length is always positive. So distance is simply just the length. Now, I'll make an example here so that you can understand distance and displacement. Now, suppose that you are to move from point A to point B. From point A to point B. Remember, you are moving to the right when you go to point B. If you go to point C, you are moving to the left. Suppose that you move from A to B, then back to C. You move from point A to B and then back to C. Let's check distance. If you move from point A to B, how many units will you be moving? 1, 2, 3, 4 units. That is the total length that you've traveled. It's 4. And then you come back, that is 4. You come back to point C. So that is 4. When you come back, 5, 6, 7, 8, 9, 10. So the distance would be 10. Because it will be given by what? It will be given by 6, 4 when you go forward, and 6 when you go back. So that would be 10 meters. I'll explain this again. If you want to move from A to B and then back to C, you want the distance, which is the total length, 1, 2, 3, 4 to B, back to C, 5, 6, 7, 8, 9, and 10. So the distance would be 10 units. But the displacement, remember now you are on point C. So the displacement should describe your position. So it's change in position from where you started to where you ended. So if you check now, your position is now at C, and at C, the position is -2. So the displacement would be equals to what? -2 meters, whilst the distance is equals to 10 meters. So the displacement would be your position. The distance would be the total length that is traveled. So with the displacement, you just check where the object is and you describe the position of that particular object. So we say that displacement has direction and distance has no direction in this case. Similarly, speed and velocity. Speed, just like distance, speed has no direction, whilst velocity has direction. But to define both of them, we define speed or velocity as the rate at which distance or displacement changes. The rate at which distance or displacement changes, which means that we will find the derivative of the displacement with respect to time. We are applying our knowledge of rates here. And then with acceleration is defined as the rate at which velocity changes. The rate at which velocity changes, which means that you'll be finding the derivative of the velocity with respect to time. Which means if you move from displacement, you'll be finding the second derivative of the displacement with respect to time. Remember, the velocity is the first derivative, then the displacement would be, or the acceleration would be the second derivative. Now, those are the concepts that we need to know. Acceleration, rate at which velocity changes. Speed and velocity, rate at which distance or displacement changes. Displacement and distance, change in position. Also, the maximum length. Also, the maximum length or the total length to which you have moved from one position to the next. Right, let us look at an example where this can be applied. Remember, if you work on a straight line, if you work on a horizontal straight line, we use concepts like displacement and distance. But if you move in a vertical direction, in the y direction, then we use height. Right, that is the displacement in the y direction and the displacement in the x direction. Now, a car speeds along 1 kilometer track, so the track is 1 kilometer long in 25 seconds. Its distance in meters from the start after t seconds is given by the function s of t is t squared plus 15t. Now, this is the objective function to determine the distance in meters. Now, if you check, we are given 1 kilometer track. So, which means the first thing that we need to do is convert this kilometer to meters. So, this would be 1,000 meters. Kilo means 1,000. So, we have 1,000 meters because in our objective function, the distance is given in meters and the time is given in seconds. So, now, write down the expression for the speed. Remember, we define the speed as the rate of change of what? Of distance. Because they want the speed, we want the rate of change of distance. How do we find rate? We differentiate. So we're going to differentiate s with respect to t. We get that this is s dash t, which is equals to 2t plus 15. So s of t in this case is our speed. the rate at which the distance is changing. So this equation is the equation that can be used to calculate speed. Now they say determine the speed of the car when it finishes there or when it crosses the finishing line. Determine the speed of the car when it crosses the finishing line. Now, if you check here, in the first question, we determined the expression that can be used to calculate speed. Now they want the exact speed when the car crosses the finishing line. Now, how long does it take the car to cross the finishing line? They said here, a car speeds along a 1 kilometer track in 25 seconds. So it takes the car 25 seconds. So we want to calculate the speed. Remember, if you can just substitute the 25 on the original equation, it would be incorrect because the original equation gives you an equation to calculate what? The distance. And the question wants you to calculate the speed. We said the speed is the rate at which the distance is changing. We found the formula that governs the speed of this car. So which means that we will substitute S of 25, which is equals to 2 times 25 plus 15. This would be equals to 2 times 25 plus 15. This should be 65 meters per second. Remember, S prime 25 is the speed after 25 seconds, but S of 25 is the distance after 25 seconds. There's a difference between S of 25 and S prime of 25. S of 25 is the distance after 25 seconds. And S prime of 25 is the speed after 25 seconds. That's very, very important. Write down an expression for the acceleration of the car after t seconds. The acceleration, remember we said acceleration is the rate at which the speed changes. The rate at which the speed changes. So the acceleration is the rate at which speed is changing. And we have an expression to calculate speed. The expression to calculate speed is S of t is 2t plus 15. This is the speed equation. But we want the rate at which that speed is changing, which means we want the second derivative. S double prime of t would be given by what? 2. That is the acceleration or the expression to find the acceleration. Moving right along. They said, hence or otherwise, calculate the acceleration of the car after 5 seconds. So we are looking for S double prime of 5. So we go back to the acceleration equation. Where we see t, we put 5. So when we see t, we put 5, and the acceleration equation was given by 2. So this would be given by what? 2 meters per second squared. Where we see t, we put 5. In this case, there is no t, which means that the acceleration is constant at 2 meters per second squared. Now they say calculate the speed of the car. Calculate the speed of the car when it is 250 meters down the track. When it is 250 meters down the track. So this question needs you to think. You are given the distance and they want the speed. They don't want the expression for the speed. They want the exact speed when the car is 250 meters down the track. So we are given the distance. We are given the distance and they want us to calculate what? The speed. So what should we do? We go back to the distance equation. Where we see 250, we're going, or where we see S of t, we put 250 because they said the distance is 250. And then we find the time it takes to cover the distance of 250 meters. After finding that time, then we'll be able to find the speed. I repeat, here we are given the speed, we're given the distance, which is 250 meters, and they want the speed. So in order for us to get the speed, we will determine the time it takes to cover a distance of 250 meters and use that time to calculate the speed, which means that now when we have our S of t is t squared plus 15t, where we see S of t, we're going to put 250. So this is 250 is equals to t squared plus 15t. This is a quadratic equation. So we're going to write it in standard form. Minus 250 is equals to 0. Now, if we look for factors, we find that this is t. The factors of 250 that can give us 15 should be 25 and 10. The 25 in this case should be positive and the 10 should be negative. So t is equals to 10 or t is equals to minus 25. Obviously, this is the time taken. The time cannot be negative. Therefore, t is equals to 10 seconds. So it takes the car 10 seconds to travel a distance of 250 meters. However, we are not looking for the time it takes to travel a distance of 250 meters. We're looking for the speed. And remember, in the previous question, we worked out the speed equation. We said that speed s prime t is given by 2t plus 15. That was the speed equation. Now, we want the speed after 10 seconds. This is 2 into 10 plus 15. So s prime of t should be given by 35 meters per second. Right, good people, we've worked out the speed of the car when it is 250 meters down the track. Now with this, we are saying we were able to work with shapes, we were able to work with graphs, we were able to work with rates, and lastly, we were able to work with the calculus of motion. Right. To summarize everything that we've done today, we say that optimization, we found that optimization is a process of modeling a situation by means of a function. We model a situation by means of a function, and then we apply differential calculus to find the input values. Those input values are going to give us the maximum or the minimum output values. Right. And then we said application of calculus can be subdivided into two main categories: direct and indirect application. Direct application is where the objective function is given, and indirect application is when the objective function is not given. We've worked with both the direct and then the indirect application in our lesson. So good people, this takes us to the end of today's lesson, and thank you very much for watching. Remember, COVID is still upon us, so you should always wear your masks, you should sanitize, and most importantly, you should always practice mathematics for you to get good maths results. Bye-bye.